Hello everybody, my name is Ferdinand Gerhardus and I'm working as EMEA Business Development Manager for Anritsu. Let me welcome you to our webinar Radar Parameter Analysis and Measurements. In this webinar, we will introduce you to methods of analyzing radar signals using different measurement instruments, including baseband processing also. This is the complete agenda for part 1 of the webinar. In this live session, we will skip some topics to keep the overall time convenient for you. Later on, you can download the complete part 1 and part 2 of the webinar from the internet. In part 2, we are focusing purely on IQ baseband processing and the relevant vector signal generators to be used. Let's jump now into the topic. The typical radars can be classified by different parameters. We have the classification based on frequency, from the very low frequency up to typically 40 gigahertz. We can subdivide the radars into different used waveforms, from unmodulated to very complex waveforms. We have radars with a high and with a low pulse repetition frequency, and we have here very much different manifold applications, military applications, civilian applications, as well as industrial applications. Now let's discuss a little bit more in depth the pulse parameters of the different radars. There are typical parameters for air traffic control, primary surveillance radar, secondary surveillance radar, maritime or meteorological radar applications. The industrial sensors are usually much higher in frequency and much higher in bandwidth. Usually, you can find information about radar signals in the public available ITU recommendation series. But be aware, if you enter into discussions about the radar frequency bands, first agree if you follow the IEEE recommendations or the NATO radar band designations. Usually, if we talk about E-band, we might think about 60 to 90 gigahertz on the background of test and measurement, because we do have the waveguide designation in mind, whereby NATO defines the E-band to be at 15 gigahertz. A radar signal is essentially a pulsed signal. These kind of signals are described with time domain and frequency domain parameters. We might be interested into peak power, average power, pulse duration, and pulse repetition frequency. These are the base pulse parameters that are tested usually. Besides ringing of the pulses, this means an overshoot or pulse droop and the duty cycle are also often measured. In the frequency domain, a pulse has theoretically an infinitive broad spectrum. Depending on the spectrum analyzer setting, we can differentiate in a so-called line spectrum and a so-called envelope spectrum. From here, we can deduct also the basic pulse parameters of pulse duration and pulse repetition frequency. The relationship of average power to the peak power is equal to the pulse duration over the pulse repetition interval. These relationships are also called duty cycle. In the next couple of slides, we want to have a closer look into weather radar operation. Here, we see the use of a short pulse for short-range observations. In parallel, we see here also moderate long pulses that are using a so-called intra-pulse modulation, also called frequency chirp. The alternating use of these pulse forms is resulting in radar reflectivity factors. This is a readout, for example, of the precipitation and is dependent on the number and the size of reflectors, also called hydrometers, like rain, snow, graupel, and hail. Looking to the below sketch, it is clear that the radar volume is increasing with distance, and the number of hydrometers is also increasing in this volume here. Many more raindrops now fit into the same rain intensity. The effective reflection area will thus also increase. Radar echoes from weather phenomena are unlike those from aircrafts, birds, or surface clutter, which tend to be individual or being a group of echoes. Echoes from precipitation take the form of a very large number of scatters per unit volume, and these particles can take on a variety of forms, including water droplets, ice crystals, hail, snow, and mixtures of the above. For this reason, and the variation in drop size distribution, it is desired to ensure a very good distinguishability between light rain, normal rain, heavy rain, and rain, for example, that includes hail. The principle of intra-pulse modulated signals allows to keep the target distinguishability high. The range resolution is usually purely dependent on the pulse width, PD, also called tau, of a radar pulse. Applying a time-dependent modulation onto the pulse while the pulse is transmitted allows on the receiver's side by the use of so-called matched filters to differentiate between targets that are within the pulse length. The compression ratio, also called time bandwidth product, enables a much higher target distinguishability. Let's recap. Short pulses are better for range resolution. Received signal strength is proportional to the pulse energy. This means RF power times pulse duration. Now it is clear that a longer pulse contains more or having a higher energy. Transmitting a long pulse that has a bandwidth corresponding to a short pulse. Energy content of long duration, low power pulse will be comparable to that of the short duration, high power pulse. Here on this slide, we can see on the left side some typical parameters of weather radars. TBP is the time bandwidth product, the result of pulse duration times modulation bandwidth. In the right column, we can see the differences of range resolution without and with pulse compression. For example, a 2 microsecond CV pulse has a range resolution of 300 meters, whereby a 40 microsecond pulse with a 3 MHz linear frequency modulation provides a 50 meter target resolution. Let's discuss now the RF energy that is needed in both cases. Here in the given example, it is required to ensure a 15 centimeter range resolution by using a pulse energy of having maximum 1 millijoule. The graphic is visualizing the idea behind. Use a sufficient modulation bandwidth and a longer pulse duration, but ensure the same pulse energy content of 1 millijoule. A pulse duration of 1 nanosecond and a pulse power of 1 megawatt would result in 1 millijoule. But a 10 microsecond pulse with a 1 gigahertz linear frequency modulation is also resulting in an energy of 1 millijoule, but with just 100 watt RF power. Not that less RF power allows for the same resolution. Also, the size of the radar is getting smaller. The power amplifier efficiency is much better compared to tube-based amplifiers in such cases. Because the resulting spectrum of solid-state power amplifiers, also called SPPA, occupies a smaller bandwidth, it is possible to operate more radars in the same area with less interference to each other. Besides pulse shaping, it is also common to use different polarization layers, so-called polarimetry radars. The use of dual polarization is one way to distinguish between hail and raindrops, for example. A weather radar follows a very specific scanning pattern. The radar starts with a ground level orography following antenna rotation, the so-called precipitation scan. Then the so-called volume scan is carried out, which is over several elevation sequences down to a quasi-horizontal position. This is then followed by several more rotations from the middle to the top, which complete the volume scan. So far, we have heard a lot of details about radar signals. Now it's time to discuss how to prove, how to measure, and how to document conducted or radiated emissions. You can imagine that the manifoldness of parameters would require a lot of manual work and operation. The MS-2840 Alpha spectrum analyzer platform provides a special measurement function. This is the MX-2840-59 Alpha pulse radar measurement function that allows the automation of these kind of measurements. The result is less error prone. The operation takes less time. Besides, the user is getting quasi in parallel a measurement report. As you can do the measurements in time and in the frequency domain, this more innovative concept is replacing older oscilloscope-based setups. Here you can get an impression about the graphical user interface of this tool. The user is just defining the basic operational parameters of the radar, getting connected, selecting the different result measurements and clicking to start. After a short while, the results are available and ready to print or available in form of a PDF report. The MS-2840 Alpha is a mid-range spectrum analyzer up to 44.5 GHz and provides an instantaneous analysis bandwidth up to 125 MHz. Together with this pulse radar analysis option MX-2840-59 Alpha, chirped signals up to a bandwidth of 30 MHz can be analyzed. The pulse widths, the pulse repetition frequency capabilities allow us to measure all common available PSR, SSR, and weather radar systems. The solution setup is completed by using the MA244XX alpha real-time peak power meter. This way, even shorter pulses can be measured. The test bench has a small footprint on the lab, an affordable, interesting price, and offers manifold measurement capabilities for signal, power, bandwidth measurements, and is also compliant with the ITU-R SM 1541-6 standard. Next, we are presenting some typical screenshots. Here we see a typical burst average power measurement. A typical pulse duration measurement. The PRF measurement shows no other modulation artifacts in between the pulses. This is a very important result. Here we see the chirp bandwidth measurement. Let's remember the TBP expression, the time bandwidth product. Here we can conclude on 1.355 MHz times 35.54 microseconds is resulting in a compression factor of 48. This here is an important measurement. It required to measure the 40 dB out-of-band rejection. This is the measurement according to the just mentioned ITU standard. The current plot displays the behavior of a solid-state power amplifier. The two markers covering a 100 MHz span, the so-called spurious domain. Here we see a typical klystron-based power amplifier. The spectral shape is much wider and unequal on either side. Here finally a real plot from a very old HB spectrum analyzer that is showing the same behavior. MS-2850 broadband FMCV radar measurements. A CV radar continuously transmits and receives simultaneously target echoes. The clear advantage is its simplicity and low-cost design. The disadvantages are borne by the reduced dynamic range due to the limited isolation between the transit and the receive path. Besides, an unmodulated CV radar can just detect a receive signal Doppler shift and does not see therefore any static object. With the help of an intrapulse modulation, range and velocity detection is possible in parallel. The purpose of an FMCV radar is therefore to measure target range, target velocity, and target azimuth. Let's consider the simplified block diagram here on the top right of such a radar system. A ramp generator is modulating an RF generator, which signal is transmitted via an antenna. The same but reflected signal is now received and downconverted to an intermediate frequency by the same as transmitted signal, low-pass filtered and sampled by an ADC, as we can see here. In a frequency over time representation, we can see in red the transmitted signal and in blue the received echo. The instantaneous difference in frequency between the TX and the RX waveforms is known as so-called beat frequency, whereby the beat frequency is the same as S times tau, with S being the chirp slope and tau the so-called round trip time, RRT, more or less the distance between the red and the blue lines. The beat frequency on the IF level the visible yellow line here, is directly proportional to the round trip time tau of the target as well as its range. Received propagation delay and Doppler frequency shift allow calculations for our above given purposes. The main concept behind any FMCW radar is a signal which is known as a chirp. The signal can be understood as a sinusoidal wave with a frequency value that increases linearly with time, as presented here on the slide as amplitude plot in the upper part and as frequency time plot in the below part. The linear change characteristic of the chirp signal creates a sawtooth-like frequency behavior. We can extract four important parameters from the given representation. The ramp startup frequency, the frequency sweep bandwidth B, which represents the frequency interval between the ramp start and the ramp end value, the chirp duration Tc represents the allocated chirp cycle time, and finally, the chirp slope S, which can be derived as B over Tc. After all these different aspects of radar and its parameters, it's now time to discuss measurement possibilities. In general, you can characterize radar signals with spectrum analyzers, power meters, vector network analyzers, or oscilloscopes. In our discussion, we concentrate on the use of spectrum analyzers and power meters and specific software options and IQ baseband post-processing tools. Usually, you need to employ mixers for down conversion for frequencies higher than 44 GHz. Harmonic and fundamental mixer technologies are available in the market, usually from companies like Eravant, VDI, or Olsen Microwave. The disadvantage of harmonic mixers can be seen in the existing image responses and the need for a higher LO power requirement. On the other side, fundamental mixers provide a very flat conversion loss response, a very broadband operating band, but they are quite expensive. FMCW radar is usually characterized by measuring the average output power, the occupied bandwidths, ramp architectures used to measure chirp time, and frame periodicity, and the linearity of the frequency sweep. In the top right picture, you can see a typical over-the-air result showing an FMCW radar with a quite flat 4 GHz sweep bandwidth. Ramp linearity measurements are important because of accuracy and resolution constraints behind, and to be able to keep the false alarm rate of the radar as low as possible. To bring the subject to more vivid life, consider the following experiment. An Anritsu MG3692 alpha signal generator, that is an old model, generates an FM modulated signal at 18 GHz with a deviation of plus minus 100 MHz in the so-called unlocked white operation mode. This signal is upconverted then to 75 GHz with a so-called quadrupler. The resulting plus minus 400 MHz sweep is measured with the MS2850 alpha that provides a maximum 1 GHz analysis bandwidth, and the IQ baseband data is saved. As already said, the signal generator is operating using unlocked white mode or wideband mode, and thus we can expect some signal anomalies that we will now try to detect. Firstly, we can see in the intensity display spectrum a sweep bandwidth of 671 MHz instead of 800 MHz. And what you see here, this plot, is the result of a so-called IQ recording. We see a section of the entire sweep bandwidth. The linearity looks good. For example, the slope of here, the visible ramp, is very, very linear and constant. Here in this section, we see clearly linearity deviations. In addition, we can observe that the change in sweep direction is not abrupt, but somewhat rounded, and this makes us lose some kind of sweep bandwidth. Why is non-linearity a problem? Such non-linearities might be caused by saturation effects or sinusoidal non-linearities. You can see that the FFT of the beat signal delivers under normal conditions a pronounced and small peak, this one here. But the width of this peak is influenced by non-linearities of the sweep. In case of TX signal slope deviations, the range and the Doppler frequencies are falsified. And this is then increasing the false alarm rate of such a radar. Think about that you would get continuously false alarms in your adaptive cruise control radar. MS-2760A based radar characterizations. Here we are now at the point to introduce finally what we mentioned beforehand. A basic spectrum analyzer for millimeter wave frequencies. The MS-2760 Alpha platform is a very special stepped FFT spectrum analyzer in the smallest available form factor and without the need for any external mixer. The model is available in two different versions. First starting from 9 kHz and going into different versions up to 170 GHz. But another special optimized version is starting at 6 GHz instead. This ultra-portable spectrum analyzer unit is focused on normal standard spectrum analyzer features. Due to the small form factor and the used non-linear transmission line architecture, the NLTL sampler is a technology that enables higher frequencies, but cannot offer us IQ capabilities. The following slides are introducing into the function principle. Finally, we are presenting some typical measurements on some FMCW radar demonstrator units. The given plot here shows a typical result in the frequency domain of a so-called Y-gig radar. This is a radar that a lot of you might have in your TVs. Here we see a typical pulse form of such a radar in the time domain. Both domains are necessary for radar signal measurements. We will observe later during a video demonstration for more details. Just take the following as a quick cookbook recipe. Go into the zero span mode and display at least one complete frame, as we see here. Apply triggering to get a stable readout and measure with markers chirp frame period and periodicity. Try to estimate also the time for a single chirp. Here you can see a typical result that shows two transmission frames. Measure the frame periodicity. Go back into the frequency mode and set the minimum capture time to be somewhat larger than the frame periodicity information that you gained beforehand. As a result, you will get the entire radar sweep and you can measure channel power and occupied bandwidths. First, we can count the number of chirps in the frame. We can see here 32 chirps. We can measure the chirp time frame period being 15.2 milliseconds. And finally, we can measure the periodicity being 33.3 milliseconds. Channel power is meant to measure average power in a selected bandwidth. You need to observe some important topics. For best accuracy, the RBW should be small compared to the integration bandwidths. To avoid any impact on the output signal of the RBW filter and detection, it is agreed to decouple the relationship RBW to VBW to a factor of 3/1. Another topic is that you need to set the trace detector to average RMS. And finally, the sweep time should be sufficient long to allow an integration period for every measurement point that is equal to the chirp repetition rate or integers thereof. The channel power measurement is especially useful for modulated, chirped, or pulsed signals that are more complex and vary their PRF or pulse widths. The spectra of these signals are more complex, and as a result, the power cannot be easily derived from the spectrum, as we explained earlier, based on a simple RF pulse. When VBW is set to linear, the average power is measured. When VBW is set to log, traditional average power is given in dBm. Let's consider a chirp with a slope of 30 MHz per microsecond. This would be equal to a 600 MHz chirp bandwidth in 20 microseconds. A typical radar parameter, and now let's use also 1001 display points and the minimum sweep time of 1 millisecond. All in all, this would allow for 50 averages per measurement point, and this is a very good setup for a measurement. Let's try to understand more the process of channel power measurements. We have tuned the SPA to see an envelope spectrum, and we have selected the specific RBW, let's say 3 MHz. We are placing a marker on top of the envelope roof, and we are reading a level of -29 dBm in the 3 MHz bandwidth. This is equal to a power of 1.25 microwatts. We have measured an occupied bandwidth of 513 MHz. This is equal to 171 power measurements with an RBW of 3 MHz. Reconverting this back to dBm results in a channel power of -6.7 dBm. Let's see if this idea and measurement makes sense. Yes, the result matches very well with -6.74 dBm channel power. Yeah, welcome to this short demonstration of the Texas Instrument AWR 1642 radar demonstration sensor. We are operating the sensor here in a typical automotive application, and we would like to show here some typical analysis that can be done with the 2760A and this kind of sensor. So first of all, we are setting the analyzer to the center frequency of 77.284 gigahertz. This center frequency has been known beforehand. We are switching then into the so-called zero span operation, because first of all we would like to get an overview about the frame periodicity and the chirp frame time. Remember, these are essential parameters that we have discussed beforehand. We are going to a level of minus 20 dBm. We are switching on the IF gain. So here we can see already some incoming pulses. Let's adjust a little bit here the y-axis scaling so that we see it in a better way. And if we are now switching over to sweep time of 100 milliseconds, we can clearly see here the different chirps of this automotive radar that are coming in. So let's now go into the trigger mode in order to make some measurements. So first of all, we are going into the trigger mode. Let's switch off here, or switch on a hold off of 66 milliseconds in order to limit a little bit the number of incoming trigger pulses. We are going to video trigger source. Let's use here a level of minus 40 dBm. And let's use here negative trigger delay of minus 5 milliseconds. So we are getting now here a stable readout. We can see here the chirp time frame. We can see here the so-called frame periodicity. And we would like to fill these figures with some real measurements in the following. So we are going to a sweep time of 40 milliseconds. We are applying here some kind of trace averaging to get the readout a little bit stable, more stable. We are switching on marker 1, and we are putting this to 0 microseconds. Now we are switching on marker 2, and we are adjusting marker 2 in a way that we can measure here really the chirp time frame. So this is around 15 milliseconds. We are switching on marker 3. And with marker 3, we would like to measure the frame periodicity. And this is the essential figure that we have to use later on in order to do some channel power measurements on the radar itself. So we are getting here 33 milliseconds. Now let's apply some delta marker settings here. And marker 3 is also delta to marker 1. And now we can switch on the so-called marker table. And we see here a chirp time frame of 15 milliseconds. We see a frame periodicity of 33 milliseconds. So these are the essential parameters that we need to recap later on if we are going back into the frequency domain in order to measure the channel power of this device. So let's now continue, and in the next we would like to get a feeling about the average power that we can detect here in the time domain. We are resetting therefore our markers. We are disabling again the trigger. And now we are setting a quite long sweep time of 10 seconds. And now let's wait for the first incoming measurement readings. This means by applying such a long sweep time, we are essentially averaging the received power more and more and more. This is kind of linear averaging, and we will see later on that this figure is corresponding and quite nice also with the figure that we can measure in the frequency domain mode. Let's really check that we have here selected on the detector peak. And now let's switch on the marker. We can read out here an average power of, let me say, minus 29 dBm. Okay, so now let's continue and go back into the so-called frequency domain. We are going back here into the normal operation mode. We are setting our sweep time again to 100 milliseconds. Frequency, last span. This takes now a while until the analyzer has switched his operational mode. And to make it quite easy, I'm just loading here. So we are loading here the so-called configuration number 2. And now we have to wait a little bit. You see, we are having applied here a sweep time of around 65 milliseconds. Remember that the frame periodicity was 33.3 milliseconds, and this is the minimum sweep time that we need to apply so that the measurements are taken long enough in order to average out essentially all the chirps and the duty cycle of the chirping radar. Let's check here on the bandwidths what kind of resolution bandwidths we are operating, 3 MHz and also 3 MHz video bandwidths. And the VBW type is linear. This means we are getting here the linear average of the incoming power. And now let's go into the measurement mode, and we would like to get a feeling about the occupied bandwidths and the channel power. Let's wait until a complete sweep has been done, and then the green dotted lines are getting updated and the below fields are filled up here with measurement results. So a complete sweep has been passed, and we are getting here as a result an occupied bandwidth of 513 megahertz, and we are getting a total received channel power of minus 8.87 dBm, so approximately minus 9 dBm. The measurement distance between the MS-2760 including this dielectrical lens antenna towards the radar is 1.35 meters. And if we are considering here at the 77.284 gigahertz frequency, a free space pass loss of minus 73 dB, then we will see later on in one of the next slides that all these figures are coming well together, and the theory and the practical measurements are more or less equal. So easy was it to measure, first of all, in the time domain, the chirp time frame, the frame periodicity, and the latter figure is essential to get a stable readout later on for the channel empowerment. Thank you for watching. Air traffic radar applications. As we can imagine, aerospace applications are very much dominated by wireless navigation aids. In general, we can distinguish between ground-based, aircraft-based, and space-based navigation and radar applications. Here in our webinar, we are focusing on primary and secondary surveillance radar applications, so-called PSR and SSR, distance measurement equipment, and on automatic dependent surveillance broadcast. Focusing means here that we are using these signals to demonstrate the measurement capabilities of different instruments. As already said beforehand in the other chapters, radar is dealing with signals that needs investigation in the time and frequency domain. So far, we have just discussed simple pulse durations and repetition rates, but the radar art is based on a complex orchestration of different PDs and PRFs. Pulse compression is just one way of tweaking the radar system to achieve the desired goals. Besides, another important branch is the measurement of the power behavior. What are the dependencies between average to peak power? How is the PI output power behaving over a longer operation period and temperature thereof? How to measure PA linearity or compression? We are not going here into the so-called code domain. We just mentioned this topic for reason of completeness. For a radar, it's not beneficial to repeat all the time the same PRF. The system might detect false target, or might get deceived, or is in case of jamming not able to differentiate between the wanted target and the jammers. Pulse stagger is one of the techniques to avoid false targets that might occur beyond the ambiguity range. Here on the right side, we see typical parameters of a modern PSR air traffic control L-band radar with different pulse durations and 3 different pulse repetition frequencies. The change of repetition frequency allows the radar on a pulse-to-pulse basis to differentiate between different returns from its own transmission systems. Returns from other radar systems with the same PRF targets beyond the unambiguous range or radars on similar radio frequency. The sketch here on the right side shows a case where a target is seen outside the ambiguous range and is therefore presented as a target on the plane position indicator, the PPI. By using a different PRF, a second sweep echo does not have a stable position to the following pulse period and is therefore detected as being wrong. The topic of PRF is a long one and we don't go deeper here. Just keep in mind that other PRF or PRI types also exist. Radar signal analysis, especially on the background of electronic intelligence, ELINT, allows us to identify based on the PRF pattern the type of radar, its application, or even its fingerprint. A fighter radar, or a marine radar, or an ATC behaves differently. So, what kind of measurement equipment do you really need? First, there's a broad product portfolio of spectrum analyzers. We differentiate between handheld spectrum analyzers and benchtop spectrum analyzers. The performance of the benchtop spectrum analyzer compared to the handheld spectrum analyzer is shrinking nowadays more and more because of the available technology allows features on handheld spectrum analyzers that have not been available beforehand. We have, for example, the MS-2090A handheld spectrum analyzer, the one on top of the 3 units here, going up to 54 GHz and providing up to 110 MHz IQ capability, either by time record, capturing, or even by streaming the IQ data via PCIe high-speed interface into other applications. The MS-2850, in the middle, is the flagship of the MS-2080XX family. With this instrument, you can capture IQ bandwidths up to 1 GHz. Finally, the latest member of the spectrum analyzer family in the 19-inch rack format is the 272XXA, again up to 54 GHz and maximum 110 MHz IQ bandwidths. In general, there are different ways to characterize radar signals with spectrum analyzers. The traditional way is going into the time domain mode. This means you are displaying power versus time. Using markers, you can measure the pulse duration and pulse repetition intervals of the pulse signal itself. Remember, we did it before. It is important that the so-called zero-span bandwidth is always large enough related to the pulse width to measure. The MS-2090A provides outstanding up to 40 MHz and the MS-2850 up to 10 MHz zero-span bandwidths. Or you can use specific software options on the spectrum analyzers to measure pulses and their behaviors fully automatically. Later, we are discussing this feature based on the MS-2090 and its 421 option pulse analyzer mode. In general, you can do the radio signal analysis live on the instrument, or you can take IQ captures that can be replayed and post-processed on the analyzer. For example, on the MS-2850. Or you can use manifold software applications either from Anritsu or third-party products. With such software, you can rerun and redisplay the signal again. This allows for a lot of measurements in the time domain as well as in the frequency domain, or using autocorrelation features to characterize the pulses of your radar signal. Power sensors have been used also in the past to characterize pulse signals, but the topic was that the power sensors lacked the sufficient rise time to follow the steep flanks of the radar signal. Nowadays, there are real-time power meters available. For example, the MA244XXA product family provides the widest of the so-called video bandwidths on the market. Using these small and price-wise affordable devices allows also to characterize very short radar signals in the time domain. These devices provide fully automatic or manual measurement modes, as well as statistical analysis possibilities that allow you to characterize power amplifiers regarding linearity and compression behavior. The oscilloscope is always somewhere in the discussions. This is due to the much higher sampling rates and very long sampling memory. Nowadays, operation bandwidths up to 110 GHz is available, but these devices are usually very expensive. These devices are not the right tool for maintenance and repair of radars and radar signals. I'm mentioning oscilloscopes just to complete the view on this topic. Aircraft navigation systems, DME and ADS measurements. In aviation, distance measuring equipment, DME, is a radio navigation technology that measures the slant range, the distance, between an aircraft and the ground station by timing the propagation delay of radio signals, typically in the frequency band between 960 to 1215 MHz. Line of visibility between the aircraft and ground station is required. An airborne interrogator initiates an exchange by transmission a pair of pulses on an assigned channel to the transponder ground station. There is a need to verify DME signal characteristics during research and development or the maintenance phase or during repair. The frequency delta between the received and transmitted signal is always 63 MHz. The channel spacing between the various DME channels are always 1 MHz. Each channel has two different codings, the X and the Y codings, which differs with regard to their pulse spacing. To limit the bandwidth of the DME signal to a channel width of 1 MHz, the envelope of the pulse is Gaussian shaped. The table shows the required parameters. Just to mention, DME can provide an accuracy up to ± 60 meters. Automatic Dependent Surveillance Broadcast, ADS-B, is a surveillance technology and form of electronic conspicuity in which an aircraft determines its position via satellite navigation or other sensors and periodically broadcasts it, enabling it to be tracked. The information can be received by air traffic control ground stations as a replacement for secondary surveillance radar, as not interrogating signal is needed from the ground. It can also be transmitted and received point-to-point by other aircraft to provide situational awareness and allow self-separation. ADS-B is, in a sense, automatic in that it requires no pilot or external input. It is somewhat dependent in that it depends on data from the aircraft's navigation system. ADS is operated in different operation modes, called A, C, and S. We will use later a so-called Mode S signal for demonstration purposes. In the next 3 slides, we are not really going into the details itself. It is meant just as an overview about the different ADS transponder operation modes. Here on this slide, we are seeing the signal pattern of the so-called Mode A. And here, we seeing the details of the so-called Mode S signal pattern. You might remember the plot from Flight Radar 24 that we have represented in the previous slide. The results on those maps are based on so-called Mode S transponder information. Such signal is received on 1090 MHz, and this is the signal pattern that we are seeing here on the slide. Important for measurements is the 1.25 microseconds period after the first 3.5 microseconds P1 and P2. At this point, it is requested that the phase change must be observed by the Mode S receiver. Otherwise, the following data block can't be detected. This is a typical example where a spectrum analyzer or a power meter can't provide this information. You need to go into the time domain with an oscilloscope. We'll show this situation later in another chapter. MA244XXA real-time peak power measurements. Although they can accurately measure CV power within the square law region, CV diode sensors cannot track rapid power changes. This means amplitude modulation, and will yield erroneous readings if power peaks occur that are above the square law region. Peak sensors use a low impedance load across the smoothing capacitors to discharge them very quickly when the RF amplitude drops. This, in combination with a very small smoothing capacitance, permits peak power sensors to achieve video bandwidths of several tens of megahertz and rise times in the 10 nanosecond range. Conventional signal processing is taking first a large number of signal samples after which without processing is done. But in the meanwhile, the power sensor is blind and is therefore lacking information from the device under test. The advantages of the real-time power processing technique can be seen on the right side. Key processing steps take place in parallel and keep pace with the signal acquisition. With no added computational overhead to needlessly prolong the sweep cycle, the sample buffer can't overflow, though there is no need to hold acquisition for trace processing. This means a gap-free signal acquisition and guarantees that intermittent signal phenomena such as transients, dropouts, or interference will be reliably captured and analyzed. For sure, it is easy to analyze an ideal and clean pulse train, but real-world radar signals might have distortions or other irregularities. The real-time peak power meter is autonomous and is gaining quasi in parallel many different signal parameters that you can see here on the screen. Although a peak power meter may seem like to be the ideal solution for measuring power of any RF signal, there are still some caveats and trade-offs. The most important issue is that the sensor's diode detector must be able to track the envelope fluctuations of the signal accurately, always. If the detector is too slow, it will not accurately follow the envelope, and there will be points in time when the carrier power is unknown. This will manifest itself as measurement errors and can be in either direction depending upon the signal and detector characteristics. The rate at which a detector can follow the envelope can be described by the rating the sensor's rise time with a pulse signal or its small signal bandwidth with an AM signal. For the given measurement example, we use the MA24418A, an 18 GHz peak power sensor with a 70 MHz bandwidth. Without any doubt, we can clearly see all pulse details on the ADS-B mode C signal. The solid yellow trace represents the measurement result. Yellow shaded areas are sampling fluctuations. The 350 kHz VBW is smearing out the entire pulse, as we see in the below plot. All information is lost. We have chosen this example to underline that the MA24418A with 350 kHz video bandwidth setting is the wrong sensor to measure a mode S signal. For the given frequency, the MA24406A with market-leading 195 MHz video bandwidth or 3 nanosecond rise time would be much better suited here in our case. Rise time and bandwidth are always inversely proportional, but their exact relationship is affected to some extent by nonlinear parameters such as slew rate, as well as by high-order filtering of the signal. For this reason, both parameters are often provided for peak power sensors. Here in another example, we can see a quadruple pulse train from the Anritsu rubidium signal generator. This time MA24406A was employed. You can clearly see the unique advantages of the 195 MHz VBW capability. However, a rule of thumb for the relationship of video bandwidth to rise time is the equation video bandwidth is equal to 0.35 divided by the rise time. Now let's see how the signal will look like when we switch to 70 MHz VBW, a smaller video bandwidth setting on the same sensor. And you can see here again that we are observing so-called round edges. This means the measurements are getting more erroneous. Pulse droop is defined as the distortion of a flat-topped rectangular pulse, characterized by a decline of the pulse top. Generally, each pulse includes an overshoot and ripple at the leading edge of the pulse and some kind of pulse droop, which is the reduction in the amplitude between the beginning and the end of the pulse. Ideally, a pulse has a constant power throughout its duration, but there are conditions where it might not be true. In high-power transmitters, such as Klystron amplifiers, it is unable to maintain full output power during a long pulse, which results in pulse droop. In solid-state power amplifiers, the primary cause of droop in gallium nitride power amplifier is the thermal response of the transistor. Gallium nitride has an inverse gain relationship with temperature. The thermal response of the transistors reduces the gain by 0.5 to 1 dB, depending on the temperature rise during the pulse. The droop is compounded with cascaded transistors, resulting in a further reduction in output power. This kind of power loss has an impact on the maximum radar range. For example, a 1 dB improvement in average power increases the range by 6%. Here in this plot, we see some kind of wanted situation. We see 5 pulses with the same pulse power. But how is the situation after a couple of thousand or a couple of 10,000 pulses? The traditional way for testing amplifier linearity is not very complex, but requires several instruments and is driving cost for test therefore. At the end of the day, you might know compression point 1 and third order intercept, often enough to know, but how is the power amplifier behaving in case that a couple of 10 or even 1,000 subcarriers are applied? For example, in case of OFDM modulation, or think about noise radar, a technology that uses noise chaotic random waveforms as transmission signal. What is the power amplifier backoff that you need to observe? What is the crest factor or the peak amplitude power ratio? You see a lot of very interesting questions. Assuming that there is a vector signal generator with auto-wide Gaussian noise available, there is just the need for 3 pieces of a real-time peak power meter to realize the measurement of forward power into the PA, the reflected power at the input, as well as the resulting output power. Herewith that, it is also possible to calculate the input reflection factor S11, and for sure also S21, the gain of the power amplifier. This is not very specific. It can be done also with other power meters. But in our case here, it is possible to measure also the multitone compression behavior of the power amplifier. Here in this case, the power amplifier is not in compression mode. You see that the input and output crest factor is more or less the same. But here, in this case, a difference of 3 dB is clearly giving proof that the PA is in compression mode. Another and better way to investigate compression situations is to plot the complementary cumulative distribution function, also called CCDF. Here in the given CCDF plot, you can see the percentage of occurrence at the input in yellow and output given in light blue is the same, meaning no compression behavior in this situation. Here the CCDF shows a difference of 2 dB pinpointing compression behavior. The MA244XXA buffer mode application enables users to make power measurements over long periods of time with essentially no gaps in acquisition or analysis. This is accomplished by real-time power processing. The application controls one or multiple sensors to capture and analyze the input signal during intervals of interest defined by the user, and discards information during non-relevant intervals in virtually real time. By discarding non-relevant information, the application will return only a single data record for each pulse, burst, or event. The data transfer is orders of magnitude less than alternatives, which require users to download and post-process large amounts of waveform trace data, causing gaps in acquisition and analysis. Here we see a typical example where a long pulse strain is captured and specific results are written into an always updated table. Thus, it is quite easy to analyze if the power remains within given limits over time and temperature, or if the PD or PIF might have some jitter, and so on. So finally, we see here a summary of different MA244XXA with relevant banner specifications. Important is that the product family provides up to 195 MHz video bandwidth, which is equal to pulse rise times of 3 nanoseconds. Up to 40 GHz, this hardware is providing even 70 MHz video bandwidth equal to 5 nanoseconds rise time. The MA244XXA is a very affordable tool for synchronized multi-channel power and pulse parameter measurements. Aircraft navigation systems DME and ADS measurements with MS-2090A Fieldmaster Pro. In this slide we can see the setup for the following measurement. A ground station SSR interrogator TX with an output power of 2000 watt is connected to the MS-2090, respectively MS-27201A, via a 46 decibels attenuator. Next, we will present in the short video clip zero-span measurements gained with the MS-2090. Short pulses, together with a low duty cycle, avoid a visible frequent display of the signal in the spectrum. The yellow trace is showing the live trace, the green is set to the max hold mode. The user can assume that there is some kind of pulse in the middle of the display, but without knowledge you might not guess that there is any useful signal. Changing to zero-span operation will change the view. Now we are operating zero-span mode with a bandwidth of 25 MHz over a time span of 1 second. You can immediately see some pulses incoming. A time span reduction down to 100 milliseconds let us see just a few pulses only. Next, we will reduce it even more down to 23 microseconds, and after applying a trigger and some averaging, we get a stable, visible signal readout with a pulse duration of 19.96 microseconds. You might remember the signal pattern of the ADS-B mode C signal. We can clearly see here a match of the signal shape, and the marker positions are confirming the correctness that would be 19.75 microseconds. Finally, we check also for the pulse repetition interval, resulting in 19.95 millisecond. A quite good match. Mode S interrogations are generated at the rate of 50 Hz PRF. Mode AC interrogations come with a PRF of 230 Hz. For sure, setting the markers more precisely would reveal even more exact values. The observed duty cycle is 0.1%. This is a very low value that could cause trouble with other instruments. By the way, this here is not a live measurement. You have seen here an IQ replay of the original signal via the Anritsu MG3710E vector signal generator. MS-2090A pulse analyzer measurements. The pulse analyzer option is fully compliant to the IEEE standard 181-2011 standard for transitions, pulses and related waveforms. This standard defines terms pertaining to transitions, pulses and related waveforms and defines procedures for estimating their parameters. When the pulse level type is set to auto, a histogram algorithm method is used for determining the high and low state levels as described by the IEEE standard. The trace data is taken as input and the amplitudes are operated in terms of dBm units. The trace data is then converted into a histogram where the number of bins is determined by a fixed bin width of 0.01 across the total range of values in the trace data. In other words, each trace point amplitude results in an incremented count in the histogram bin that corresponds to the amplitude range in which that amplitude falls. The best case resolution of the resulting amplitude can be as low as 0.01 dBm and depends on how much the overall level fluctuates. Instants are a specific time value within the waveform time duration, and they are typically referenced relative to the initial instant of the waveform. What takes place afterwards could remind us of a tiresome topic in high school, namely the topic of curve discussion. Here you identify high, low, and turning points and can use them to describe the shape of the curve. Something similar happens here with the pulse analyzer software, only that pulses, pulse widths, pulse repetition rates, and pulse power levels are calculated here. Here on the slide, we see a typical result. Across a 10 milliseconds time frame, you can see several pulses with equidistance. The dotted lines and trace marks indicate the before described statistical points. All measurements are gained fully automatically. You can see here a summary of the power-related measurements. You can see here all pulse-related parameters. And if you are really interested in detail, you can find here the point transition characteristics. Here we see a typical pulse measurement result of the before shown airport surveillance radar at 2.875 GHz. Zooming into the time axis also allows to isolate a single pulse, as we see here on the screen. Again, all measurements are completed accurately and quickly without interrupting the operation of the device. For sure, you can enlarge the screen to see the signal itself in a greater detail. Finally, we are presenting again our ADS-B mode C signal in a short video demonstration. We can see a pronounced CV-like signal at 1030 MHz and adjust all parameters in a way to see the signal in a good shape. After switching to option 412 pulse analyzer, we are seeing firstly again the previous -20 dB carrier. Immediately after switching on the modulation on the radar transmitter, we see within a default time span of 1 second several pulses traveling on the display. By adjusting the sweep time to 40 microseconds and initiating triggering, we see immediately the well-known shape of the mode C pulse pattern. Applying some averaging is stabilizing the trace readout. Next, the user would adjust the time axis to see at least 2 pulses. As a result, the pulse characteristics of the entire pulse form would be measured. Again, this measurement was an IQ replay to make it easier for the purpose of this webinar here. This was part 1 of our webinar. We are looking forward to welcoming you again in part 2. Thank you for watching. Thank you for listening.